today. So pretty much today is going to be a recap of some sort. We are going to essentially do a recap on requirement analysis, on design, using the vehicle of the set of diagram available from UML. Again, as I mentioned many times, you are not bounded to UML at all. In fact, the history of UML itself also tell you it's just a tool for you to use, and not something, not a religion you should buy into, essentially. So it was actually assembled together by basically say, hey, what are the possible representations available today in software engineering? Let's lump them together, called something called unified modeling language. So pretty much they didn't invent any of those notations in the first place. The only thing they did is put everything together, call it something called unified modeling language. So the way you look at this should be, guess what? You are there to see whether there is some notation which is going to help you. Some figures are going to help you communicate your requirement, your design, your high-level design, your detailed design. Okay, that's it. You are not bounded to any of these languages or notations or figures. The most important thing for you is actually trying to come up with your own notation, set of notations. You select from this and say, hey, this is my simplest way to communicate my design. Eventually, if you join a team, you have to adapt to the culture of the team. And actually the way that people communicate in terms of requirement, design, and even code, comments, differ for different teams. Okay? So this is just for you to come up, have something say, hey, this is my way of playing basketball. I mean, if I join a team, I have to adapt to the style that team already have. Or if I'm starting a team, then I can actually infuse my style to be the dominating style, right? The same idea here. If you have a you have a process, you set out notation, you think it's effective and comfortable. That's you have to get something in place like that when you're in school, and then you have to have your open mind about joining a team, adapt to their way of doing things. Okay, certainly not the way that happened about 15 years ago. Everybody go out and buy a lot of UML books and trying to learn UML. I think that's the only way to you can do things. You'll quickly find out that they are just a set of notations. It's not the way of doing things. It's still, you have to come up with the requirement. You have to come up with the design. You have to come up with the code eventually. All right. Okay. So let's see. So it's not a methodology. It's a lump sum of figures, way of writing things people find it useful in software engineering from very beginning. Okay. For instance, things like a class diagram. I don't think these folks who put the UML together or center together, they invented a class diagram. Actually, people have been drawing a box and line diagram for like ages, right? Probably even from the beginning of human being, people are already doing this kind of design, right? Not for computer program, I'm sure, but for other things, right? When they build a fort, they pretty much have to do this, right? Say how many gates I need to have, and how many watchtower I need, and those kind of thing, right? The same thing, right? So you can't say, oh man, computer science invented a class diagram, and the diagram of box and lines. No, that's not something we can claim. It's essentially something we adapt from existing things that people find pretty useful, then we put it in our design document, our requirement document, so that we can do the job easier. So again, many things in computer science education, software engineering is to map your skill set you already have, and just map it into software development process, and you know when and how to use them. So we'll look at this diagram as we go. Basically, they form a recap of what we have been learning. So this is, there's a standard group on this called the Object Management Group. Used to be huge, right? So when I was an undergraduate student, this is huge, right? Together with the rise of object-oriented programming, particularly C++, and later on Java, so object management group was pretty big about 20, 15 years ago. But later on, because they put together a too complicated scheme, end up to be nobody using it. Okay, because it's way too complicated. So basically people say, wow, there's no way we can master the whole thing. Guess what? We're just going to take whatever worked for us and run without using your name. And this documentation is just way too many things. It's not a language. It's just a set of useful tools. All right. So here, let's start with first useful things, which is what we use to represent our high-level design, and also as a vehicle for a detailed design, a class diagram. I mean, this is something, no matter what kind of methodology or process you have to do, you would have to come to this, right? Because this directly maps into code. In your code, you would have to define class, right? So what is a class? Class is actually a type. So what's the difference between entity and type? What is the difference between entity and type? The same idea with instance and class. What's the difference between, you guys have been learning languages for decades, right? I mean, for the last 2 years at least, right? So what's the difference between entity and type? What's the relationship?
The entity is an item of a type.
That's right. Type essentially is a summary of features, characteristic of a set of entities. And an entity of the type essentially is say, okay, this entity has all the attributes and characteristic of that type, right? For instance, bank account. Your bank account is not my bank account, and my bank account is not your bank account, right? But they are all of the same bank account type. If you go to a bank like Wells Fargo. Certainly they have different type of bank account for sure, but if you're in the same kind of bank account type, you have all the features like anybody else in the same type. Okay? So this diagram is not invented by UML. It's just, UML just say, hey, guess what, guys? This diagram is used for representation of class. So you should use it. That's the only thing UML did. Okay? What they did is not to invent this diagram, but just to say, okay, this is something used for your object-oriented design. That's all. For bank account, well, you have this. Certainly you need to have a name, right? You have to map this to some name. And most importantly, you have the data, and you have actions on the data. Okay? So this actually reflects the most fundamental concept in computer science, which is you are processing data. You are processing data, right? So initially, the only job computer is doing is to crunch number, processing data. And just happened to be, we found out many ways to encode tasks into number crunching, data processing. Okay? At the very beginning, just computer is a computer. To compute, add numbers together, multiply, and so forth, summarize them together. Okay? Until somebody came up with the idea, guess what? For controlling the lights in this system, that can be cast as crunching numbers. Then we find better use for computers. Okay? But fundamentally, you are looking at data and actions, operations you can take on those data. That is also nature of object classes, right? This is the class definition. Basically say any bank account you're going to create will have account balance attributes. To save the data, we'll have two methods called deposit and withdraw. Certainly there are many other things that if you go to a real bank account with Wells Fargo, they have many, many other operations they can do on this, right? But that's just adding more features to it, okay? But fundamentally, you got data and you got operation. So in this sense, again, UML didn't invent this. The only thing UML people did is say, hey, we select class diagram as a good representation of your system component. That's all they did. All right, so this is, you have some freedom on notation, but this is just, you need, the only difference here, the important information on this page is you need to be able to differentiate a type and an entity, an instance and a class. Okay, class basically representing a set of instances with the same attributes and characteristics, with the same kind of data and same kind of operation. Okay, you have to. So that's the difference. That's why in your language you instantiate, create an instance of a class. Okay, you're not creating a class. You're creating an instance of the class. Your class is actually a type. Similar to your float, similar to your integer, similar to your Boolean. Those are built-in types. Array built-in types. Okay? Class is a way for you to define new types. Okay? New types. So here you have many other. So an interesting thing that you may find useful is actually those prefixes. So for instance, here we know that for class we have, particularly in Java, you have private members, right? You have public members, right? So those are very useful because private member means what? Okay, this is not something you can access from outside. And those two methods are made public, which is basically saying, hey, this is the interface you can use to access my data. Why is that important? So this is the important concept called information hiding or encapsulation, which means that, okay, if you want to withdraw money and deposit money, you can only do this way, according to my way. Okay, if you make this public, basically any other entity in your program would be able to say, I directly assign to the value of your bank account. Okay? What's the problem with that? If I can circumvent the ATM machine, I can circumvent all the tailors, I can circumvent online banking, but I can get to your bank account balance. What will happen?
You'll modify it.
Yeah.
Like,
You're saying it in a very nice way. You're going to modify it, right? I mean, the way I'm going to, so basically this is called, that's why people rob banks. That's why people are stealing from bank accounts. The same thing happened here, right? So the goal is to protect this data. So you can only have two ways. The normal way to access my account information, not other way around. Okay? So this is actually one step further, better than the C programming language. C programming language, basically, you have no protection like this from your compiler. This is essentially something, in C program, if I'm in the same program as you, I can actually access any data, global. Right? So this is, if your information is there, okay, if I don't use your methods, no, I'm not going to be able to look at your code, look at your data. Certainly this one will not guarantee that there's no way you can get to this number, but this is just from compiler-wise, at least you can keep people from making mistakes. Okay? If I'm malicious, I'm going to do more, right? I'm going to do other kind of attack on you to get the information, not only just, I'm not even in your, need to be in your program. All right, so one thing that we haven't talked to code a lot would be the relationships between your classes or objects of that classes. For instance, here is an example. We can actually say the static relationship of a set of classes. So this is basically say, okay, on the higher level, what are the relationships between your classes? Okay, for instance, this diagram is basically saying that my car should have a chassis, should have an engine, which is not true anymore. When you have electrical cars, you don't really need an engine, you just need motors, right? I mean, wheels still necessary, but otherwise I am driving a tractor instead of a car. You better have seats, right? Otherwise, how I'm going to use the car, right? So you can see that now this can become an optional thing, but you have a relationship basically. Hey, so there's the kind of relationship, sort of relationship between chassis and the car and so forth. Okay, so there is no actionable thing here yet, right? So say this is not something that have direct mapping into some sort of code, right? This is conceptually for you to better understand the relationship of your class and your among your classes, okay, statically. You have other relationship like another way is you can actually add on implicity, basically say, okay, have more stronger information. Basically, this is giving more information to your class diagram. Say your car should have one chassis. I mean, have two will be really weird, right? So for have one engine, that's not necessary anymore. That could be actually can be E0 now, right? I mean, the wheels, I mean, sunroof and all these things. Basically, say okay, just to keep information. This is how you can, if you want to represent this kind of information, enforce this kind of information, you have a way to put on your class diagram. Or put it in a stronger way, you have compilation. Compilation is stronger. Basically, this is say, okay, by compilation, you are actually requiring, 64 squares on your chessboard. Okay, so this is okay. If you're missing one, that's not a board. That's not a complete board. If you want to complete board, you better have 64. Right? So that is stronger relationship. It's essentially say, okay, if you're going to have one, you're going to have all of them, right? So here you can see this kind of relationship is only mainly for information, for you to represent concepts. Okay, it may not have direct implementation in code, but sometimes you do, right? For instance, in this case, this is something you have to enforce in code. Otherwise, your code is incorrect. When you instantiate a chessboard, then you have to have 64 squares enforced in code, right? Otherwise, it's incorrect. So some of this information you have here, multiplicity and actually are enforceable. Some of them are not enforceable, or you don't necessarily want to enforce, but you do. You can actually enforce them in code. Okay. So this is to say, okay, how many components we have, their relationship. Okay. That's it. So that is for your class diagram. All right. The other type of relationship we commonly see in object-oriented design is actually inheritance. Okay? Inheritance is, remember, our class is a type. Right? Type means summary of all the attribute characteristic of group of things. Integer, right? You have unlimited number of integers. Right? But you know integer must have some kind of characteristics. Right? 3.2 is not integer. Well, 1 is an integer, right? This is something you learn. I mean, in grade school, but to prove this, actually you have to go to the PhD program and beyond, right? But for us to use, I mean, we know, okay, this is type. The type should be like this, right? So generalization inheritance is a way to abstract things. So is this totally necessary for your code? No. But this is a better design. So we can talk about design, whether we can talk about correct design, incorrect design, good design, not so good design. All right? You can have a design which is correct, but not so good. Right? However, if you have an incorrect design, there are no ways it can be good. Because you did something wrong, either you are missing features, or totally your design wouldn't implement the feature you identified. Right? Either way, you have an incorrect design.